Okay, so we are now starting part A of homework 4 for process dynamics and control. And our part A is going to be split up between two parts. For now, we're working on a single tank, not three tanks. And for this, we have a tank, as you can see here, with a cross-sectional area. I labeled that as AC with the liquid feed QN that is drained by the gravity at the bottom of size, which is across a cross-sectional area of our hole, right? And we're going to be essentially deriving a first order transfer function related to the Laplace domain liquid level, capital H, and feed rate Qn. So essentially, we're using this Laplace transform. I went ahead and kind of uh, put out the equation already for that, as well as our Taylor series, which we're going to be using to linearize our ODE. Okay, so this is the subtraction of the initial steady state solution and the Laplace transport of deviation variables, which we'll get into. Okay, so we're going to go ahead and start this. Again, we have our tank and we have our height, as you can see here. Try to use my pointer finger. We have our height, as you can see here. So it kind of does show. Okay, cool. So we have our flow rate coming in. We have our Q in coming out, flow rate coming out. We have the both cross-sectional areas of the tank and the hole, and we have our height listed. Okay. So now what we want to do is we want to essentially solve for the change of our change of hmm, okay, so we're going to be solving for the change of volume over the change of height. So let's go ahead and start with that. So change of volume over change of height, which is essentially going to be equal to the cross-sectional area of our tank times the change of height over change of time. Okay, this is also going to be equal to Q in minus Q out. And again, if you know from previously other videos, we've again and again listed Q out as the cross-sectional area of our hole times 2 times gravity times height. So keep that in mind. We can now go ahead and rewrite this equation. So again, cross-sectional area of our tank times the change of height over change of time. And we're going to kind of write this essentially as a more generalized form. So we're going to, again, have Qn. But for this term right here, we're going to go ahead and write it as HB, okay? And reason being is where we have B equal to the cross-sectional area of our hole times gravity over the square root of 2 times gravity times height. Okay, so we can now go ahead and rewrite this essentially using our initial steady state to utilize Laplace transform. So we're going to be utilizing initial steady state using this Laplace transform equation. Okay, essentially. Yep. Okay, so we're going to be saying that our height is going to be equal to HS. So this S is essentially just saying it's at steady state, and we can go ahead and do this uh, for Qn. So Qn, our flow rate coming in is going to be equal to Qn comma S. So essentially this is what our new steady state variables are, okay? So we can now look at this for our deviation variables. So we can say that H bar, let's go ahead and line this up. So H bar is going to be equal to our height function, height as a function of time, subtracted by the height at steady state, okay? And we can do this again for our flow rate. So Q bar in is going to be equal to our Q in at a function of time minus our Q in at steady state, okay? So these are essentially our deviation variables. Okay. So now what we can do is utilize our Taylor series expansion. So let me go ahead and write that. So we're now using Taylor series, okay? So let's go back and look at our function right here, right? We have our function of a, which is equal to our function of x, which is equal to our function of a plus our f prime of a multiplied by our x minus a, okay? So let's go ahead and do that. So we want to essentially linearize our height. So let's go back again and look at our problem. So we um, want to essentially linearize our ODE subtraction of the initial steady solution and our Laplace transform of deviation variables, okay, that we just found. Okay, so we can say that our square root of h is going to be equal to the square root of the height at steady state, uh, which essentially is still at steady state. And this is going to be equal to 1 over 2 times the square root of our height at steady state multiplied by our h bar of our function of t. Okay? All right, so now using Laplace transform, we can essentially, use this equation that we have up here again. So we're going to be using this equation right here. Okay. So let's go ahead and kind of copy and paste. That might be a little bit easier. Okay. We're going to essentially be using this equation again. Okay, it's not letting me copy and paste. Weird. Okay, so let's just go ahead and rewrite it again. So we have essentially the cross-sectional area of our tank times the change of height over change of time. In this case, we're going to be using h bar, which is going to be equal to q bar minus our b function that we introduced times our h bar. Okay, so now using this Laplace transform, we can utilize these variables, specifically s. So let's come back down here and see what we have. We can rewrite this as a cross-sectional area of our tank times our S times our H bar, our big H. So again, remember we are looking at this liquid level H, okay, which is replaced with our Laplace, essentially. So that's where we finally introduced this variable, and it's going to be equal to our Qn of our function of S minus our b times our big H as a function of S. Okay, so we now want to rearrange these variables and solve to find our liquid level H. Okay, so we're trying to find this variables essentially. Okay, so rearranging this, what we get is H times the cross-sectional area of a tank times S plus B equal Qn. So what we can do now is rearrange this variable. What we get is H equals 1 over, this term over here, we're dividing it out. So AC times S plus B, and this will be multiplied by Qn, right? Okay, so again, I want to re-explain what B is in this case. So we have where B is equal to the cross-sectional area of the whole times gravity divided by our square root of 2 times g times h. Okay? So essentially, this is our final equation, but we want to get it in terms of our transfer function. So let's still go ahead and box this right here, okay? Okay, so in terms of our transfer function, what we get is k over this tau function of s plus 1. And rearranging this, what we get using our b variable is 1 divided by b over our cross-sectional area. So we're reusing this equation of h, so which will be AC, essentially putting in this equation, right? So AC over b times s plus 1. Okay, so what we essentially get for our final equation is using this transfer function is H is going to be equal to 1 over B over, again, using this term now, our tau S plus 1 times Qn, where our tau is going to be equal to AC over B. Okay, so this is essentially our final equation for our transfer function. We can go ahead and now move on to the second part of part A. All right, so finishing out part A of this homework. This is the second part. So for this, we're looking at three identical gravity drain tanks in series. We're going to be deriving the transfer function relating the Laplace domain flow into the first tank Qn and Qn and the third tank H3. Okay, so essentially we have our first flow rate coming in. We have that first height. We have the area of our cross-sectional area of the tank. We have the area of the hole. And then we have these other flow rates, Q1, Q2, and Q3, and as well as the other ones, H1, H2, H3. Okay. So we're going to see how this flow rate coming in essentially changes the height of each tank essentially, especially that last tank. And we're going to kind of be referencing this using a block diagram. Okay. So I want to first start out by using our linearization that we derived from the last part, which is essentially going to be, okay. So from the last part, which is essentially starting with Q out, which is the cross-sectional, the area of our hole times 2 times gravity times the height at steady state. All right, this is going to be added to the area of our hole times gravity divided by the square root of 2 times gravity times the height at steady state. And this is going to be multiplied by h bar. Okay. So essentially, this steady state is approximating our value of Q out. So we can also kind of we also know from the last part that this is essentially B, which is our proportionality constant. And we know that B is equal to area of our hole times gravity times the square root of 2 times gravity times the height at steady state. Okay. So what we want to do now is essentially use our proportionality constant to relate the height of all of our three tanks to our Laplace domain. So to relating the tanks to our Laplace domain essentially. Okay. The tanks to our Laplace domain to our height, essentially. There you go. Okay, so we also know from the last part, we looked at the liquid level H. So essentially H is equal to 1 over B divided by, I forgot what that was. So let's go ahead and reference this as H1. We're going to be looking at H1, H2, H3. So we want to know kind of what each one entails. So 1 over B over tau S at steady state plus 1 multiplied by Qn. Okay, so that's the essentially the equation that we derived, and tau is equal to AC over I forget what tau is exactly equal to, but we put in tau back into this. Okay. So let's go ahead and based off of this graph, we can see these tanks we can see here. We're going to be using a block diagram to show how our flow rates coming in relate to our liquid level equation and how those liquid level heights relate to our proportionality constants and so on. Okay. And from these block diagrams, we're going to essentially get an equation for H3, the liquid level in the third tank. Okay. So starting with these block diagrams, we're going to first be looking at Qn, which is essentially equal to Qn, which is essentially equal to 1 over B over our tau S plus 1. Okay. So essentially, right now we're on our first tank, right? But now we want to relate this this tank to this tank's height to our proportionality constant. So we can say that our H1 is related to our B. So H1 times B is what we're looking at in this case, right? So from this, we can look at our second tank. So Q2, no, sorry, go ahead and look back at that. Yeah, so now we're looking at right here, right? So we're looking at that right there, okay? So Q1, and again, in this block diagram, we're gonna have our, essentially our H2 equation. So H2 is 1 over B over tau S plus 1. And from this, we can see that H2 times our proportionality constant. And from this, we can be looking at our second to third tank. So Q2, and we're going to again have our equation of 1 over B times 1 over B divided by tau S plus 1. Okay, so from this, we can then actually we can now be looking at H3. So essentially, this is what we're trying to find using these block diagrams, right? So now if you want to kind of craft up an equation for this, we can say that H3, again, we're going to be kind of canceling things out. In this case, we're going to be canceling out our proportionality constants. We're going to kind of be crossing out our, we're going to still have all of these tanks. Okay, we're going to have all of these tanks, and we're going to have our Qn flow rate, right? So all the other flow rates are going to kind of cancel out. So Q1 and Q2, as well as our other height. So H3 is going to be equal to Qn times 1 over B over tau S plus 1. However, because we're looking at 3 blocks here, we're going to want to go ahead and put this to the power of 3. Okay, so essentially this is the equation that is derived to find our liquid level of this tank. Okay, essentially this. We want to find this liquid level, which is H3. Okay, so yeah, that sums that up. Let's go ahead and move on to part B.